Okay, assalamualaikum and good morning. Okay, this is the continuation video for chapter 3 angle modulation transmission and reception part 2. So in the previous video, I stopped at subchapter 3.6 deviation ratio. Okay, and in this video, we will continue with subchapter 3.7 until subchapter 3.11. Okay, so basically for this part, chapter 3 part 2b is more on the theoretical side on the FM PM modulator, transmitter, receiver, and also demodulator. Okay, so I don't expect you to like basically for this part, what you need to know is that, for example, you need to know the types of modulator, types of receiver, transmitter, and also the process of each component briefly. Okay, so I don't expect you to like to be able to write the process in detail, but in general. Okay, so now let's start with the subchapter 3.7, which is FM and PM modulator. Okay, so stated here, a phase modulator is a circuit where the carrier instantaneous phase is proportional to the modulating signal. Okay, so if you look at here, okay, so this is the phase modulator, PM modulator, and this is the carrier instantaneous phase, theta t, okay, is proportional to Vt. Vt here is the modulating signal amplitude, okay. So for the frequency modulator, it is a circuit where the carrier instantaneous phase is proportional to the integral of the modulating signal. So different from the phase modulator, FM modulator is the carrier instantaneous phase is directly proportional to the integral of the modulating signal. That's why you have the integral Vt here. Okay. So now stated here, if you consider the FM modulator, if the modulating signal is Vt is differentiated before being applied to the FM modulator, the instantaneous phase is now proportional to the modulating signal or PM modulator. So what this statement means is that if, for example, you have a FM modulator, okay, and you know that FM modulator, the carrier instantaneous frequency phase is directly proportional to the integral of Vt. Okay, so now you have an FM modulator, but you add a differentiator in front. So now you have a differentiator plus FM modulator. So what happens is that, okay, what happens is that now you have, because you have a differentiator, so now your modulating signal become dVt over dt. Okay, and then for FM modulator, you know that theta t is directly proportional to the integral of Vt, and your Vt now is dVt over dt. So if you integrate the dVt over dt, you will get this equals to Vt. Okay, and the result will become theta t directly proportional to Vt. And you can see that this statement here is the same as the ones in the PM modulator. Okay, so in conclusion is that if you have a FM modulator and you add a differentiator, you will get you will have a system which will act as a PM modulator instead. Okay, so different for the, if you have a PM modulator, okay, if you have a PM modulator and you add an integrator, okay, so now you will have theta t directly proportional to integrate integral of Vt. Okay, so if you compare this, okay, it is actually the same as Fm modulator, which is theta t is directly proportional to the integral of Vt. So that's why we can say that if you have a Pm modulator with the addition of integrator, you will actually have a Fm modulator. It's the same as Fm modulator. Okay. So now let's look into types of FM and PM modulator. Okay, so for FM modulator, basically we can divide it into two types. Okay, the first one is direct FM modulator. The second one is indirect FM modulator. Okay, for subchapter 3.7.1, this is direct FM modulator. So it said that with direct FM, the instantaneous frequency deviation is directly proportional to the amplitude of the modulating signal. Okay, so this is direct. So if you frequency deviation directly proportional to the amplitude of the modulating signal. And this figure here is the schematic diagram of a simple direct FM generator. Okay, so this is your sound source, your signal, your input signal, and then you have a microphone, embedded capacitor in the microphone CM, and then you have an inductor, and you have an oscillator, and your output is here. Okay, so the combination of the capacitor and the inductor is we call it as a tank circuit. Okay, and it acts as a frequency determining components. Okay, so over here stated that the tank circuit, which is consists of the inductor and also the capacitor, is the frequency determining section. Okay, and the CM is a capacitor inside the microphone. The function is to convert acoustic energy into mechanical energy. So remember, your sound source, your original sound source is in acoustic energy, and then the capacitor will convert it into mechanical energy. So when it already converts into mechanical energy, okay, it will in turn vary the distance between the plates of the CM. Okay, so when the distance of the plate of CM varies, it will consequently changes the capacitance value of the CM. Okay, so as the CM is varied, the resonant frequency is varied. Okay, so that's why we said that the oscillator upper frequency varies directly with the external sound forces. Okay, so if the external sound forces, meaning the input varies, then the oscillator output frequency will varies. Okay, so basically for direct FM modulator, we have several types of direct FM modulator, and the first one is the varactor diode modulator. Okay, so this is the circuit for varactor diode modulator. Okay, so R1 and R2, this is R1, this is R2, will develop a DC voltage where it will reverse bias the varactor diode VD1. Okay, this is the varactor diode. Okay. After that, it will determine the resonant frequency for the oscillator. External modulating signal voltage added or subtracted from the DC bias will changes the capacitance of the diode and consequently changes the frequency of the oscillation. So basically the process is similar to the standard direct FM modulator that I've already explained before. Okay, So when you have the external modulating signal, you have the input source. This will actually changes the capacitance. Okay, and when the capacitance value changes, it will consequently changes the frequency of the oscillation. Okay, so now let's look at here. We have positive alternations and negative alternations. So during positive alternations, the modulating signal will increase the reverse bias of VD1, and thus it will decrease the capacitance, and the frequency oscillation will increase. Okay. Different from the negative, during negative alternation, the modulating signal will decrease the reverse bias of PD1 and in turn increase the capacitance, and it will decrease the frequency of oscillation. Okay, so this varactor diode modulator, the advantages is that it is simple, it is stable, and it is reliable. However, it has a limited peak frequency deviation, thus it will result in a limited use to the low index application. Okay, it can only be used for low index applications. The second types of direct FM modulator is the VCO FM modulator. Okay, so this is the circuit for VCO FM modulator. So if you want to calculate for the center frequency of the oscillator, you can use this formula where Fc is equals to 1 over 2 pi square root LC. L is the inductance, C is the capacitance. Okay, so when a modulating signal is applied to the VCO FM modulator, okay, there will be changes in terms of its capacitance. Okay, therefore we will have value for delta C. So delta C is the change in varactor diode capacitance due to modulating signal. So you need to remember the process of for both VCO FM modulator and the previous varactor diode modulator is basically similar, okay, as the ones that I already explained during the section 4.7.1 direct FM modulator. So basically when you have a modulating signal, it will changes the value of the capacitance, then it will changes the value of the oscillator frequency. Okay, so same for this one. If you have a modulating signal, you will have a change in the capacitance. So you will have a value delta C. Okay, so now you can calculate for the new oscillator frequency Fc. Okay, so your formula is 1 over 2 pi L multiply C plus delta C square root. Okay, and now you can calculate for the change in frequency where delta F is equals to Fc minus F. So Fc is the new oscillator frequency and F is the previous oscillator frequency. This one, 1 over 2 pi square root LC. Okay, and then you can calculate for the change in frequency delta F. So next, let's look into indirect FM or direct PM modulator. So we know that if you have a PM modulator and then you add a, if you have a PM modulator and you add an integrator in front, you will actually have a FM modulator. So that's why we call this as indirect FM modulator. Okay. For indirect FM, the instantaneous phase deviation rather than instantaneous frequency deviation is directly proportional to the modulating signal. Okay, so if you look at here for indirect FM, instead of looking at the instantaneous frequency deviation, it looks into instantaneous phase deviation instead. Okay, so instantaneous phase deviation is directly proportional to the modulating signal. So the indirect FM can be accomplished by directly changing the phase of the carrier. So this is the schematic diagram of an indirect FM modulator using a varactor diode. Okay, you have your modulating signal input here, and you have a crystal oscillator carry input, and this is your output. So remember the concept of a modulation, you have two inputs, modulating signal and carrier signal. Okay, so this is modulating signal and this is the carrier signal and this is the output. So the process of indirect FM modulator is that the varactor diode VD1 is placed in series with the inductive network L1 and R1. Okay, so this combined series parallel network appears as series resonance circuit to the output frequency from the crystal oscillator. Okay, so the modulating signal is applied to VD1 where it will changes the capacitance and subsequently changes the phase of the impedance seen by the carrier. And the result, there will be a corresponding phase shift in the carrier. So the advantage of using indirect FM modulator compared to direct FM modulator is that it is more stable. However, it has a more distortion. Okay, so even though it is stable, it has more distortion. So to decide whether you want to use indirect FM or direct FM, it depends on your application. Okay, whether you want a more stable system or you want a system with a higher accuracy, low, meaning less distortion. Okay, it depends on your system. So next subchapter 3.8 is the frequency up conversion. So remember, if you remember your communication block diagram, basically you have a modulator, you have a transmitter, you have a channel, and then you have receiver, and you have a demodulator. So frequency up conversion is the process after modulation. So after you have modulated the signal, okay, frequency of the modulated wave will be up converted to a desired frequency of transmission in order to transmit the the signal through a channel. Meaning you want to up convert it or you want to increase the frequency. So there are two methods of frequency up conversion. The first method is we call as heterodyning process. The second method is the frequency multiplication. Okay, so let's look into the first method, which is the heterodyne process or heterodyne method. So this is the block diagram of a heterodyne method. So this is the input from your FM modulator or PM modulator. So you have FC, your carrier frequency, you have frequency deviation delta F, you have your modulation index M, you have your modulating frequency FM, and you have your bandwidth. Okay. So you want to up convert the frequency, you want to increase the frequency. So for the heterodyne process, to increase, to up convert the frequency, it introduces a RF oscillator, buffer amplifier, balanced modulator, and also a band pass filter. Okay, so what it does is that basically it RF oscillator will generate a new frequency, which we call it as FRF. Okay, so this frequency will be added to the frequency of, from the FM modulator or PM modulator here. Okay, so the output here will become your new FC, your FC out will become FC in plus FRF. Okay, the frequency that we generate using the RF oscillator. However, if you look at here, the other parameter, delta F, modulation index, modulation frequency, and also the bandwidth remain unchanged. The only frequency, the only parameter that is changing is the carrier frequency, FC. Okay, so that's why it said here, the frequency deviation, rate of change, modulation index, phase deviation, and bandwidth are unaffected by the heterodyne process. Only the carrier frequency is affected. So your FC new or your FC out now is equals to FC in plus FRF. Okay, so that is the heterodyne method. The second method is the multiplication method. So for multiplication method, you only need one new component, which is the multiplier. Okay, and you have a n. It depends on your application, the value for n. So this is the input from FM or your PM modulator. Okay, and the output, since you have a multiplier here, your output, for example, for your carrier frequency, your output will become n multiply with FC. Okay, so n multiply with FC in. So you will get the FC out. Same for the frequency deviation. So delta F out is equals to n multiply with delta F in. And also for your modulation index M out, n equals to M in. Okay. However, your modulating frequency is not changing, is not affected by the multiplier. Okay. So if you look at here, if since your M out here is affected by the multiplier, meaning your modulation index will increase. Okay, because it's multiplied by n. So if when your modulation index increase, okay, automatically the bandwidth will also increase. That's why B out, the bandwidth out, is higher than the B in. Okay, so that's why it's stated here, as frequency division and modulation index are multiplied, the number of side frequency also increases, thus the bandwidth also increases. Okay, so if you want to calculate for your B out, okay, you can use this formula, the Cousins rule formula, already explained in the previous video. So B out equals to N to delta F or N B in. So next, let's look into the FM transmitter. For FM transmitter, we also have two types. The first one is direct FM. The second one is the indirect FM transmitter. Okay, so this is the direct FM transmitter block diagram for a commercial broadcast band transmitter. So we also call this direct FM transmitter as the Crosby direct FM transmitter. Okay, because it includes what we call as automatic frequency control, AFC loop, this one. For direct FM transmitter, we have the AFC loop. Okay. Stated here, the carrier frequency is basically the center frequency of the master oscillator. So your carrier frequency FC is 5.1 megahertz. Okay, which is multiplied by 18 to produce a final transmission carrier Ft equals to 91.8 megahertz. Okay, so the carrier frequency here is multiplied by 18. So that's why you have 3 multiplier, 3, 2, and 3. So 3 multiplied 2 is 6. 6 multiplied 3 will become 18. Okay, so if you multiply 5.1 megahertz with 18, you will get the Ft equals to 91.8 megahertz. The frequency and phase deviation at the output of the modulator are also multiplied by 18, okay, because it uses the multiplier method. So stated here, to achieve maximum deviation allowed for FM stations at antenna, which is 75 kilohertz, the deviation at the output of the modulator is delta F is equals to 75K divided by N. So your frequency deviation is basically 4166.7 Hertz. Okay. And your modulation index, okay, you know that your modulation index M equals to delta F over Fm. M equals to delta F over Fm. So your delta F is 4166.7 divided by Fm. Okay, and your Fm for the maximum modulated signal frequency allowed for Fm is 15K. So you divide with 15K, you will get your modulation index equals to 0.2778. So remember for direct FM transmitter, we have the AFC loop. Okay, why this AFC loop is very important is because to overcome the problem of stability. Okay, stated here the stability of the oscillator in direct FM is low. That's why to overcome the problem, AFC loop is used. So this is very important. If a question asks you the function of AFC loop, you must be able to answer that the AFC loop is to overcome the problem of stability in direct FM transmitter. Okay, only for direct FM transmitter. For indirect transmitter, you don't need to use the AFC loop. So this is the indirect FM transmitter. Okay, this is the block diagram. We also call this as the Armstrong indirect FM transmitter. Okay, the indirect FM transmitter is where the phase deviation is directly proportional to the modulating signal. Okay, and you can see that now for the indirect FM transmitter, the carrier oscillator is not directly divided, thus you don't need to use the AFC loop in order to maintain the stability. Okay, so now let's look at this block diagram. Okay, so this is your modulating signal FM, and this is your carrier signal, crystal carrier oscillator, FC equals to 200 kilohertz. Okay, and what happens is that this FC and FM we go into the combining network, and then you have a bandpass filter, and you have several multiplier and bandpass filter over here. Okay, and then this is your output to go to the channel. Okay, so this slide, this equation is the equation for the standard modulated signal for angle modulation. Okay, you have seen this before in chapter 3 part 1. So MT is equals to VC cos omega CT, plus m cos omega mt. And by using the trigonometric function where cos A plus B is equals to cos A cos B minus sin A sin B, you will get this equation. Okay, so cos A plus B, so the A here is omega ct and the B is m cos omega mt. Okay, so that's why you will have VC cos A cos B minus sin A sin B. Okay, so stated here, for a small modulation index, meaning m very small, okay, which is m almost equals to 0. So when m equals to 0, so if you key in your calculator, cos 0 is equals to 1. So this m cos omega mt is equals cos 0 will become 1. Okay, and sine 0 will become 0. So that's why your mt, your latest mt will become mt equals to Vc or cos omega ct minus Vc m sine omega ct cos omega mt, where Vc cos omega ct is the original carrier, Vc sine omega ct is the phase shifted carrier, and cos omega mt is the modulating signal. Okay. So now let's look at this example. Consider a 200 kHz carrier being phase modulated with a 15 kHz modulating signal producing modulation index of 0.00096. Okay, so basically, okay, so this is FC, this is FM, and this is your modulation index M. Okay, so the frequency deviation of the output of the combining network, you know that M equals to delta F over Fm. So delta F is equals to M Fm. Okay, and you will get the frequency deviation equals to 14.4 megahertz. So in order to achieve the required 75 kilohertz deviation for the FM broadcast at the antenna, the frequency must be multiplied by approximately 5,208. However, this would produce a transmission carrier antenna equals to 1041.6 megahertz. And you can see that this value is beyond the limits for the commercial FM broadcast band, which it should be around 30 to 300 megahertz only. Okay, so basically what this example explains is that, okay, for FM broadcast, again, you need to achieve a 75 kilohertz deviation at the antenna here. Okay, you need to achieve 75 kilohertz deviation at the antenna. Okay, so since so your carrier signal is 200K, so in order to achieve 75K at the antenna, you need to multiply approximately around 5,208. But if you multiply the carrier frequency with 5,208, your frequency will become 1,041.6 megahertz, which is beyond the value limits for the commercial FM broadcast band. Okay, so that's why you need what we call as the indirect FM transmitter. So for indirect FM transmitter, if you look at here, for indirect FM transmitter, instead of directly multiply it with 5,208, you have several multiplier. You have 72 multiplier and another 72 multiplier over here. Okay. So now let's calculate. So let the output waveform of the network is multiplied by 72. Okay, so this is the first multiplier, 72. Okay, the first multiplier, 72. This is 72. Okay, so your F will become 72 multiplied with the 200 kilohertz, will become 14.4 megahertz. And then your modulation index is also multiplied with 72, and same for your frequency deviation. Okay, the signal is then mixed with the 13.15 megahertz crystal control frequency to produce a different signal F2 with the following characteristic. So if you look at here, you have a mixer and down converter with a crystal oscillator frequency of this value. Okay, so that's why, okay, because you have a mixer with the crystal control frequency of 13.15 megahertz here, your F2, the value from this 14.4 megahertz, the new value for the frequency will become 14.4 megahertz minus 13.15 megahertz, and it will become 1.25 megahertz. Okay, and your modulation index and delta F is remain unchanged. And then the output of the mixer is once again multiplied by 72 to produce the transmit signal with the following characteristic. So you look at here, okay, after the mixer and down converter, you have another multiplier with n equals to 72. So that's why the F now is equals to 90 megahertz after you multiply it with 72. And your modulation index is 4.98, and your delta F is 74.65 kilohertz. Okay, so if you look at here, your frequency is now 70 megahertz, and your frequency deviation already satisfy the requirement for 75 kilohertz. Okay, so this you get 74.65 kilohertz. Okay, and your frequency is also between the range 30 to 300 megahertz. This one is 90 megahertz. Okay, so you can see the difference when you use an indirect FM transmitter. Okay, so you can achieve delta F 75 kilohertz, and your frequency is also between the FM broadcast band 30 to 300 megahertz. Okay, subchapter 3.10 is FM receiver. So this is the block diagram for a double conversion super heterodyne FM receiver. So it consists of pre-selector. This is the pre-selector. You have the RF amplifier. You have the first and second mixer. You have the IF amplifier. Okay, so all of these components, the function is the same as the one in the AM receiver in chapter 2. Okay, so these components, okay, these components we call it as the AGC, automatic gain control. The function is used to prevent the mixer saturation when strong RF signals are received. Okay, and then over here we have the audio detector stage, which consists of limiter, demodulator, and the emphasis network. So the limiter here, the function is to remove the amplitude variation caused by noise, which is one of the AM's drawback. Okay. And then the frequency discriminator or the demodulator will extract the information from the modulated wave, and then the de-emphasis network will improve the signal to noise ratio. Okay, so if you look at this block diagram, you have the first intermediate frequency and second intermediate frequency, first IF and second IF. So the first IF is relatively a high frequency, because in order to get a good image frequency rejection, while the second IF is a relative low frequency that will allow the IF amplifiers to have a high gain. Okay, so the FM demodulator is a frequency-dependent circuit designed to produce an output voltage that is proportional to the instantaneous frequency at its input. So FM demodulator is basically the inverse of FM modulator. Okay, and the output of the FM demodulator is given by V out equals to KD delta F, where KD is equals to V over F. Okay, and the most common circuit used for FM signal demodulation are the slope detector, balanced slope detector, and also PLL demodulator. So now let's look at example. So the example stated that for an FM demodulator circuit with a transfer function of Kd equals to 0.2 volt kilohertz and an FM input signal with 20 kilohertz of peak frequency deviation, determine the peak output voltage. Okay, so you can use the previous formula in the previous slide. So you have V out T equals to Kd delta F. Okay, so your Kd is 0.2 volt over kilohertz, multiply with 20 kilohertz. Okay, so you can cancel the kilohertz. So 0.2 multiply with 20, you will get 4 volt. So your peak output voltage is equals to 4 volt. So subchapter 3.11.1 is a type of FM demodulator. So this is a tuned circuit frequency discriminator. Okay, for I think for this part, you can read the process or for each demodulator by yourself. Okay, you just need to know that basically for this part, you just need to know the process in brief. Okay, how the demodulator works. Okay, for different types of demodulator. So this one is the slope detector. And this is the balance slope detector. Okay, and okay, so based on this this slide. Okay, this is the conclusion. Okay, the difference between the slope detector and balance detector. So for the slope detector, even though it has a simpler circuit, but the balanced slope detector is better in terms of linearity and tuning, and it does not need a limiter stage, okay, to compensate the amplitude variation. Okay. So basically, if you compare between slope detector and balance detector is better. However, it has a more complex circuit. Okay. So same for this part, the PLL FM demodulator. I think you can read the process by yourself. Okay. The process of PLF demodulator, okay, by yourself. So basically, for chapter 3, part 2B, like I said before, this is more on the theoretical side. You don't need to really go into detail the process of each modulator, demodulator, transmitter, and receiver. Okay, just know in brief. Okay, and but the most important things you need to know is that maybe the difference between indirect and direct. Okay, this part, the first part here, is important. Okay, so the others is that you just need to know types of, for example, types of indirect FM transmitter, direct FM transmitter, and so on. Okay, and also the process in brief. Okay, so that's all for chapter 3, part 2B, and we will continue with a new video for chapter 3, part 3. Okay, thank you.